Hello all, welcome to the AI driven perception learning and mapping for drones course. This is the tutorial 4, which is introduction to PyTorch. Now in this particular tutorial we will discuss about different types of deep learning frameworks. Essentially, why do we require these frameworks, what were the earlier frameworks that existed, and why do we prefer PyTorch more. Once we know different types of the frameworks, we will talk about tensor manipulation. So essentially, since we are we know more about linear algebra, we are comfortable with vectors and matrices. However, when we are working with deep learning models, for us tensors are essentially very important. So we will try to go over certain basic tensor manipulation operations, and we essentially, as a homework, more of these operations could be performed. Essentially, the goal is to be very comfortable with the increasing dimensions of a tensor. So if we look at matrices, it is essentially a rank 2 tensor. However, when we are dealing with rank 3 and rank 4, essentially how can they be visualized and what happens when we reshape them. These are some things that we will discuss in the tensor manipulation part, and finally we will talk about the Autograd functionality in PyTorch. Essentially, whenever we are going over neural networks or single layer perceptron or multi-layer perceptron, there are essentially two steps. One is the forward pass, which is using the current set of weights trying to predict the output of the particular neural network, be it a single layer perceptron or a multi-layer perceptron. And once we have the output, we can calculate the loss and essentially update the weights using gradient descent. Right now, Autograd is something that takes care of this particular functionality in PyTorch, and we'll maybe go over one example where we'll try to see what is the functionality of Autograd. And in the next tutorial, we will focus on essentially writing a deep, or essentially defining a model, training it on a particular data set, and again observing the functionality of Autograd, which is available in PyTorch. Now essentially, what are deep learning frameworks? Deep learning frameworks are software libraries that provide building blocks about neural networks. So we have observed different types of operators used in the neural network. For example, we have seen activation function, we have seen convolution layers, we have seen the pooling operation. Right now, whenever we define any neural network, these are fundamental blocks in this neural network. However, instead of defining these layers from scratch in, let's say, Python, and then writing its backpropagation, there are deep learning frameworks available. Now, however, it can be done in Python. We can write, and we do write, custom operators and layers and define its derivative. However, deep learning frameworks are essentially tools which already have these functionalities defined, right? Hence, these can be used to define the building blocks of neural networks, right? Now, designing, training and deployment is made easy using these deep learning frameworks, and essentially tasks like automatic differentiation, GPU acceleration, tensor operations and so on, these tasks are also made easy when we are using different deep learning frameworks. Now essentially, all these deep learning frameworks use CUDA. CUDA is essentially NVIDIA's computing platform. Now what CUDA does is it runs these tensors on a GPU, right? Now let's take a look at this particular figure. Essentially, we have different types of frameworks. It could be Python, it could be TensorFlow, it could be JAX. These are essentially different types of frameworks available. We will focus more on PyTorch. However, there are other frameworks which are available and can be used. Essentially, these give us APIs. So for example, any neural network operators such as convolution or pooling could be used using these frameworks. Essentially, if we use torch.nn, it defines a lot of these operators which could be used in the neural network. Now once we have defined our model, essentially what would happen is that this framework would push all of this into the NVIDIA GPU. Using CUNN, using CUDA drivers, this would be deployed on GPU, and once it is deployed on GPU, it would essentially run these operations on GPU, right. When we use deep learning platforms, we have either a possibility to use CPUs or to use GPUs, and essentially we do not use CPUs, we essentially work only with GPUs. Now these frameworks is a very easy way for us to have an interface or to work with CUDA, which is essentially NVIDIA's parallel computing platform. Now a practical takeaway is that every matrix multiplication, every convolution, every activation could be easily defined with these deep learning frameworks, and once it is defined in using these deep learning frameworks, it could be deployed onto the GPU. Hence forward pass, backward pass, updates of weights, optimization and so on can be done in a very easy way. Now let us take a look at some of these frameworks. The first one is PyTorch. PyTorch is essentially the most popular framework. It was similar to TensorFlow, where there was a time when people used to use PyTorch and TensorFlow both. However, with time PyTorch has been accepted widely across the whole community. It is essentially because it builds upon Python, and it's a very easy way to deploy deep learning models. So we don't have to define different types of graphs and all, we just define the layer as we will see in the next tutorial, and the optimization is pretty easy, right. Now one more benefit of PyTorch is that it has a dynamic computation graph. Now similar to PyTorch, there is also TensorFlow. TensorFlow was essentially very useful and very widely used because of the scalable deployment and the facility to deploy it on mobile device, right, on edge support. However, the community has now slowly moved on to PyTorch, right. This particular figure essentially explains the concept of computation graph. Now if we look at this graph, we can see that the neural network could be written as weight times the input plus bias, right. This is essentially how we have been defining our perceptron models, right. Now we can see that for a given input we have a weight W, and when we do a matrix multiplication, finally we will add it with the bias term, and once we have this particular part, which is W into X plus B, we will pass it through the ReLU activation function, essentially defining the output, which is Y, right. Now this is essentially the graph that is made for a particular model, or in our case just a perceptron, right. Now essentially this is also something that we observed in the backpropagation part of the this is also something we observed when we were trying to derive the backpropagation and weight update for single layer and multi-layer perceptron, which is we saw that once we had an output Y and a corresponding error, we saw how the weights was updated, right, and essentially we tried to derive those weights mathematically. However, with these deep learning frameworks, the update is automatic. Essentially the updates, the delta W which is computed is done using these deep learning frameworks. Now there is also Keras, which was also widely used. It's still used because of its user friendly interface. So in case anybody is starting with these frameworks, Keras does provide a very intuitive way to define these components. However, now it has been integrated with TensorFlow. Now lastly, there are also other types of frameworks, for example JAX and PaddlePaddle. PaddlePaddle is essentially a very strong framework which is used in the Chinese ecosystem, right, and the earlier deep learning frameworks essentially were Theano and Caffe. Theano was developed in the University of Montreal, and Caffe was developed by the Berkeley AI Research. Okay. We also have MATLAB, which is also one of the popular frameworks. Essentially what MATLAB does is it provides an integrated environment for the whole processing, which is essentially from data annotation, data pre-processing to model design to model training to visualization to deployment, etc. Right. Now, how MATLAB does is slightly different, as in it has a deep learning toolbox. Using this deep learning toolbox, we could design the neural networks. We can also train these neural networks, and we can essentially visualize and debug what is going on. MATLAB also has a GPU acceleration facility, right. So, similar to how we saw in earlier frameworks, essentially MATLAB has a MATLAB's toolbox where we can design our models. Once these models are designed, they could be deployed using the deep learning toolbox. There is a facility of compatibility with CUDA, which is provided by NVIDIA, and hence all the training and inference could be deployed on the GPU. Okay. Now, let us start with the introduction or understanding of tensors. Right. Let us start with a very simple example of defining a scalar. So, a scalar could essentially just be a number which could be, let us say, 2 here. Now, essentially we define this as a rank 0 tensor, right, because it has only one value. We can also look at a vector which is, for example, say 2, 3, 4, and essentially since it is a vector, it only has one axis. Since it only has one axis, it is essentially a rank 1 tensor. So, now what do we mean by rank? Rank essentially means how many independent directions or how many axes are needed to describe the data. Now, for the example of scalar, there essentially is no need for a axis. I can just write it as 2. However, when we are dealing with vectors, we need to write it as 2, 3, 4. Essentially, it requires one axis. If we look at a matrix, which we will look at in the next slide, we can observe that it could be used to define using 2 axes. Now, let us define or initialize the tensor, which is a rank 2 tensor, which could also be defined using a matrix. So, the example here is the matrix which is 1, 2, 3, 4, 5, 6. Essentially, there are 3 rows and 2 columns, and hence it is a rank 2 tensor, right. Now, there are other examples that there are different examples that we can think of which could be defined as a rank 2 or rank 3 tensor. For example, if we look at a grayscale image essentially is a matrix because we have the height and width and the number of channels is 1, right. So, it is only one feature map. Hence, it is just a matrix, which is why it is a rank 2 tensor. If we look at RGB, it essentially has 3 channels, which is why it is a rank 3 tensor, right. Now, an illustration of rank can be observed here. Essentially, rank 0 is for a scalar. If we are dealing with rank 1, it is essentially defined using one axis. If we are looking at rank 2, it is essentially a matrix. And if we are looking at rank 3, it is essentially using 3 independent axes, which is x, y and z, right, and this is why it is rank 3. Now, this is just for visualization purpose. Another example for illustration is if we look at the vector here, which is 2, 3, 4, we can see that it has essentially one axis and it has 3 elements in that particular axis. Similarly, we can look at a matrix which has a shape of 3 and 2 with random elements filled up in the matrix, right. Now, let us take a look at a 3 axis tensor. Now, a 3 axis tensor could be defined as, let us say, shape of 3, 2, 5. Now, let us perform a random initialization, right. If we perform a random initialization of this tensor, essentially we would get something which is observed on the left figure. Now, all the elements in this particular tensor are randomly defined or randomly initialized. So, we are not very worried about what are the elements that are there in the tensor. We are focusing more on how it could be represented. Now, when we are dealing with 3 axis tensor, we observe that there are 3 axes, right. So, we can observe that there is an axis which is specific to the axis 2, and we can define on this particular axis 3 different maps. Now, when the shape is 3 to 5, we can essentially visualize it in the first figure. We can essentially stack it and visualize it in the second figure, and once stacked we can change the view and we can observe it in the last figure, which is essentially the same tensor, which is a rank 3 tensor, but we are trying to look at it with different types of visualization, right. Now essentially once we have randomly initialized these tensors, now the operation could be any operation and the elements could be any elements, right. For example, we could have elements which are floating point numbers, we could have integers, we could have complex valued numbers, we could also have strings which are part of these tensors, right. And when we have tensors defined, we could essentially perform tensor operations, which could be element wise addition, multiplication or matrix multiplication, right. Now let us try to work with PyTorch and try to define a rank 3 tensor. Now when we are working with PyTorch, it is important for us to import torch, which is observed in the first line, right. So when we import torch and we have an environment that has been built up using PyTorch, we can essentially use PyTorch, right. Now to initialize a rank 3 tensor of, let us say, shape 3 to 5, what we can do is we can define tensor is torch of zeros of this particular shape, right. And what this would do is define a rank 3 tensor with the shape of 3 to 5. All the elements in this particular tensor would be zeros, right. Now we can print the tensor, which is essentially what it would print that all the values in the tensor, and we can print the shape. Essentially tensor dot shape would give us the shape of the tensor, right. Now let us say we do not want all the elements to be 0, then what we would do is we would essentially use torch dot rand, which is essentially doing a random initialization, or we could do torch dot ones, which is essentially defining all the elements as 1, right. Now these are different ways to initialize, right. So we essentially have a rank 3 tensor. The rank 3 tensor could have values which could all be 0, could be random initialization, could be ones, and there could be other types of initializations that could be used, right. Now let us take an example and see what it means when we are doing a tensor operation on a rank 3 tensor. So let us say that we focus on a matrix multiplication for a particular axis, right. So the tensor 1 has a shape of 2, 3, 2, the tensor B has the shape of 2, 2, 2. Now when we perform a tensor multiplication across an axis, essentially what we are trying to do is we are trying to multiply the matrix across different axes. For example, if I try to work around the axis 0, what we would do is we would try to multiply the matrix 0 in tensor A with matrix 0 in tensor B and get the value as matrix 0 in the tensor C. Similarly, we could take the matrix 1 in tensor A, we could take the matrix 1 in tensor B, and we could multiply and get the value, right. So essentially we can define across which axis we want the matrix to be multiplied. However, the fundamental rules of matrix multiplication are still in place. Essentially we can't multiply across any axis because there may be a shape mismatch, right. Okay. Now let us take a look at some formal definitions. When we are dealing with tensor shapes, some of these names are, so shape essentially means the length or the number of elements in a particular axis, right. Rank is essentially the number of tensor axes. We saw some of the examples in previous slides. The axis is essentially the particular dimension of the tensor. And lastly, we have the size, which is essentially the total number of items in the tensor, right. Now let us say that we are dealing with a rank 4 tensor. For example, it could have a shape it could have a shape of 3, 2, 4, 5, right. Now when we are dealing with this sort of a tensor, if we have this shape, the first shape essentially starts from axis 0 and it goes on to the other axis. So we can say that axis 0 essentially has 3, axis 1 is 2, axis 4 and so on, right. Now the visualization of a rank 4 tensor can be observed on the figure in the right. Now again, this is just a visualization of a rank 4 tensor, right. It could be viewed in different, it could be viewed differently also. We only focus on one particular view. Okay. Now let us start with a rank 4 tensor which could be defined with a shape of 3, 2, 4, 5. Now for this particular shape, let us assume that all the elements in this particular tensor are of float 32 data type. Now this data type can change, it could become complex, it could become integer, etc., right. This depends on the way we are initializing, right. Now the number of axes in this particular rank 4 tensor is 4. The shape of the tensor is essentially 3, 2, 4, 5. Now the elements across axis 0, which is across the first axis, is 3, right. The elements across the last axis, which is essentially -1 axis, is 5. The total number of elements, that is the total number of elements in the rank 4 tensor, are 3 into 2 into 4 into 5, which is essentially 120, right. Now this is something that we have done in for a rank 4 matrix, for a rank 4 tensor. This is something that we have done for a rank 4 tensor. Now we can follow the same procedure and do the same things for a different rank. So say rank 1, rank 2, rank 3 and so on. Essentially the procedure or the names, which is essentially the number of axes, the elements across the axis 0 or the last axis, these nomenclatures remain the same, only the rank keep changing. Okay. Now let us try to focus on indexing of tensors. So let us say that we have defined a rank 3 tensor. This rank 3 tensor could essentially have a shape of 3 to 5, right, and the visualization is observed on the left figure. Now let us say we only want to focus on this particular part, which is essentially to index the tensor with semicolon comma semicolon comma 4, right. Now essentially when we are doing that, we are focusing on the last part of this tensor. So for when we are printing this particular command, which is print rank 3 tensor of this particular index, we observe that the what it returns is 49, 14, 19 and 24, 29, essentially the last parts. Now this is one example of a tensor indexing. There are other tensor indexing also, and hence it is recommended to look at certain tensor indexing operations, right. This would make you more comfortable when we are dealing with different type of indexing operations. Now let us take an example and focus on the reshaping of tensor shapes, right. Now reshaping essentially is trying to create a new shape with the same number of elements, right. However, one caution is that we need to respect either the order of the axis or we need to preserve the information in the particular axis, right. For example, let us take a rank 3 tensor. In a rank 3 tensor, we can essentially visualize it in this first figure, right. Now if we reshape it, the reshape could essentially try to expand each of these axes, right, and we could have this sort of a representation, or else we can have reshape 2, which is essentially just stacking each axis on top of each other. So we had axis 1, 2, 3, we can just stack these axes, right. Now we are in all of these operations respecting the order of an axis, either the order or we are preserving the information of these axes, right. Now this is one reshape operation where we are trying to manipulate the shapes and trying to create the tensor with the same number of elements but different shape. Now there are some bad examples as well. For example, the first figure, which is essentially trying to reshape the tensor, however it does not preserve the information in the axis, right. So we can see that the elements 10 and 1 are now with the 5, 7, 8, 9, which is essentially from a different axis, right. So we are not respecting or preserving the information in the axis, right. We can also have this sort of a reshape which is observed in the middle figure, where we can see that there are certain elements missing. Now whenever there are functionalities in PyTorch and other deep learning frameworks where if we reshape it, we can essentially stack it with say zeros or 1 or some dummy number. However, we are still not preserving the axis information, right. Axis 1 essentially was from 0 to 9, the axis 2 is from 10 to 19, and now it is part of the same axis, right. So it is not preserving the information, and this is also observed in the reshape 2 operation, right. Okay. Now lastly, there are certain tensors such as a string tensor. String tensor is essentially the data is stored as a string. Okay. Now let us focus on the Autograd functionality in PyTorch. Now whenever we are training a neural network, essentially there are two steps. The first step is that once we have defined an input and it passes once we have defined an input and it passes through the neural network, we have an output prediction, right. Now in the forward propagation, the neural network essentially takes the input and tries to make the best guess, which is essentially trying to make the output prediction, right. Now once this is done, essentially there is also a backward propagation step which is very important. In this step, essentially the neural network adjusts its parameter which is proportional to the error, which is essentially using gradient descent to update all these parameters, right. So W is equals to W minus eta dou E by dou W, right. Now essentially it does this by traversing backwards from the output. It is essentially collecting the derivatives of the error with respect to each of these parameters, right, and this is using the chain rule trying to update each of these weights which is available in the neural network, right. Now to do all this, we require something known as Autograd, which is automatic differentiation engine. Now torch.autograd is essentially this engine which is used for neural network training. Now Autograd calculates and stores the gradients of each model parameter in the Autograd essentially calculates and stores the gradient of each of these models, right. So it does this using the grad tool. Now when dot backward is called, Autograd calculates the gradients and stores them in the respective tensors dot grad attribute. Essentially what we are trying to say is W minus eta times dou E by dou W, right. Now essentially when we do dot backward, the weights are updated for each weights in the neural network. Now how it does is essentially trying to come up with a computational graph. Autograd keeps the record of the data tensors and all the executed operations. Now once it has a record of these operations, it defines a graph which is known as directed acyclic graph. Now once the acyclic graph is defined, when we do dot backward, essentially it computes the gradients using the chain rule, right. Now this is something that we have done for both a single layer perceptron and a multi-layer perceptron. Autograd does it by computing a graph, right. Now when the backward pass essentially is used using this graph, it computes the gradient which is the delta W, it essentially updates the weight, and once it has updated the weight, it would essentially try to make the delta W as 0. So this is just to initialize it to 0, right. So we will compute the error, compute the delta W, which is the gradient. We will update the weights over the whole model. Once this is done, we would make delta W as 0 and start all over again. Let's observe the operation of the graph using an example. So let's look at this code, which is essentially a PyTorch code. Now we define a tensor x, which is torch.tensor. The requires grad is true, which is essentially we can compute the gradients for this particular tensor. Now we perform a certain operation and define y, which is the x square. Once we have defined y, we will essentially do y dot backward. When we do y dot backward, it would calculate the gradients and it would update the components of this operation, which is x, right. Now how does the directed graph look? Essentially when we are performing a forward pass, right, we are taking a variable x which has requires grad true, which is essentially saying that the gradients on this particular variable x can be performed. In case we had gradients true as false, this gradient update would not happen, right. Now when we have x, we define the operation which is essentially just a square operation and we get y, right. Now this is the directed acyclic graph which is doing a forward pass. So essentially we start from input and we propagate towards the output. And once we have propagated towards the output, for a neural network we would essentially compute an error. Since this is not a neural network, this is just a mathematical operation, we will not use the error here. Now let us take a look at the backward pass. When we are looking at the backward pass, which is essentially when we do y dot backward, we will try to go from output to the input, which is essentially. Now once we have y, we will try to calculate the gradient of this operator and then update x, right. Now we know that the derivative is essentially 2x, right. So we have the derivative. Once we have the derivative, we can update the value of x, right. Now one caution here is that when we are doing gradient update, we need to follow something known as gradient accumulation and clearing, because if we focus on this, which is the first backward pass, we do y dot backward. When we perform y dot backward, it is essentially doing a gradient computation, right. So we are trying to essentially calculate delta x, right. Now when we do a second backward pass, right, so what would happen is this delta x would essentially contain the value of the old and the new update, which is why we always perform delta grad as 0, which is essentially after the operation is performed, after the backward pass is performed, we make the delta x as 0 and then perform the step. So it is forward pass, backward pass, clean up the gradients, repeat. Okay. To summarize, essentially in this particular lecture or tutorial, we went over an introduction of various deep learning frameworks. We understood what do we mean by and what are the existing deep learning frameworks, how it works with the NVIDIA CUDA support. We also went into a very brief description of tensor manipulation, which is essentially defining different rank of tensors. Once these tensors are defined, we followed different operations on these tensors. Lastly, we also understood the Autograd functionality of PyTorch, which is essential in both the forward pass as well as the backward pass. Once this gradient update is done, it is important to clean up the gradient, which is essentially clean up delta x or delta w, whichever is the weights, and then again perform a forward pass and update. Thank you.